Hello, another divisibility problem which will be more difficult, more interesting, and I will show you two different methods of proving some statement. Let's start. Proving divisibility without using induction, problem number 2 in this section. And now we have to prove that for each natural number n, the number n to the fifth minus n is divisible by 30. And now 30 is equal to 6 times 5, so it is 2 times 3 times 5. 2, 3 and 5 are all prime numbers, and they are relatively prime by this. And this means that we can separately discuss divisibility by 2, 3 and 5 and combine these three together into divisibility by 30. And before I start showing you the solution method, or two methods, I would like to remind you of this one. This you know already. Every second integer is divisible by 2, every third is divisible by 3. So if we have a group of 3 consecutive integer numbers, one will be divisible by 3 and at least one by 2. Because, well, it depends if you happen to take such a 3 or such a 3. So it will be 2 or 3 numbers which will be even. And what about divisibility by 5? Here you have 5 possible remainders in division by 5. It can be 0, 1, 2, 3 or 4. And again, every fifth integer number is divisible by 5, and then such a number can be written as 5 times k, where k is some integer. Every fifth number has remainder 1 in division by 5. So these will be these numbers, which can be written as 5 times some integer plus 1. Remainder 2, 3, 4. And you see that everything is used here. All the numbers are taken, which means that if you would have remainder 5, then in fact it's the same as remainder 0, but instead of k you take k plus 1. So just 5 possible remainders. Okay, now we are prepared, and now I will solve this problem. And this particular problem was not included in my course about proofs by induction, but sure you could prove this statement by induction, so you can do this if you want to. And now I will start by writing down here a common part for both method 1 and 2, and then I will continue with two methods separately. So first remark is that 30 is equal to 2 times 3 times 5, right? And these three numbers are prime numbers, so I can examine divisibility by each of them separately. You know this from the previous lecture, right? And I will start by factoring n to the fifth minus n in the following way. First I factor out n. I don't have much choice, right? This is the only thing I can do. And in the parentheses I will then have n to the fourth minus 1, right? And now I can apply my favorite formula. A squared minus b squared is equal to a minus b times a plus b. This time with, maybe I will move it slightly to the left, this time with a equal to n squared, because you see I have n to the fourth, and this is n squared squared, and with b equal to 1. And when I apply this formula in this way, I will get n times n squared minus 1 times n squared plus 1. And I can still factor this one by applying the same formula, but this time with a equal to n and b equal to 1. So this will give me I will maybe take it in parentheses so that you see that it's another case, because it doesn't look elegant when I first say that a is equal to n squared and then I say that a is equal to n. These are two separate cases, right? Okay, so now I can factor n squared minus 1 as n minus 1 times n plus 1, right? And as previously, I can change order of these factors so that I see that I will have n minus 1 times n plus 1. So you see this n squared minus 1 is here and here. The product of these two is n squared minus 1. And then I still have n squared plus 1. So altogether I see that my number n to the fifth minus n factors as n minus 1 times n plus 1 times n squared plus 1. And already from this, I can conclude that this number is divisible by 6, right? Because I have here the product of 3 consecutive integers, right? And you know that exactly one of them is divisible by 3 and at least one of them is even. So this means that divisibility by 6 is okay. Divisibility by 6 is okay, because we have this product of 3 consecutive integers in factorization of our very number. So the only thing what is left is to show that our number is divisible by 5. This is the only thing which is left. And this I will prove in 2 different ways. And then when you work on your own, you can just choose your favorites. Okay, so now my first method will be by further factoring my number. So you see, I know that every fifth integer number is divisible by 5. But I have here 3 consecutive integer numbers, right? n minus 1 and n plus 1. And it would be really cool to have 2 more which stand next to these 3. Which would it be? It would be n minus 2 and n plus 2. Let's have a look. Let's have a look, maybe another color to make it clear that it's kind of a side computation. So if I now take n minus 2, this is the integer which is coming before n minus 1, and n plus 2, this is the integer coming directly after n plus 1, then again, from my favorite formula for the difference of 2 squares, I have sum and difference of two exactly the same terms. It will be n squared minus 4, right? I know this. But in my factorization, I have n squared plus 1. You know, I can apply a very cool trick on it. I will do like this. I write here that my n to the fifth minus n is equal to n minus 1 and n plus 1. And then instead of writing n squared plus 1, I will write n squared, and now look at this, it will be really cool. Now I write minus 4 because I want to have minus 4, but I kind of don't have. I have n squared plus 1. So in order to make it right, n squared plus 1, I have to add 5. You see? So in this way, I subtracted 4 and added 5, so I actually just added 1. So it is really my number. But now I can split it. I can split this factor into 2 pieces. So it's kind of inverse distributive law. So what I will do now is the following. I will split this last factor into n squared minus 4 and then afterwards plus 5. So first, this one is multiplied by n minus 1, n plus 1, and then the second, so maybe I will mark it here with orange, that they are coming from this factor which I split, right? And this 5 must also be multiplied by n minus 1, n plus 1. So this is what my number n to the 5th minus n is equal to. If you don't believe it, just verify it by taking, for example, this common factor, factoring it out, and in the parentheses you will get n squared minus 4 plus 5, which is exactly n to the n squared plus 1, so everything is just fine. But now I'm almost done, because now I can factor n squared minus 4 into n minus 2 times n plus 2, and in between I can squish this n minus 1, n plus 1. And then I have a product of 5 consecutive integer numbers. And then, of course, I have to add this remaining part, n plus 1. And now I'm actually done, because you know what? Here, this part is divisible by 5, as it is a product of 5 consecutive integers. And the second one is divisible by 5 because it has factor 5. It is 5 times some integer. So it is obviously divisible by 5 because it is 5 times some integer. And the sum of two numbers which are divisible by 5 is divisible by 5. So we are done with the first method. It's nice, right? And now the second method. So here again we are starting by that we know that our n to the 5th minus n is factored. I have factored this like it is n minus 1 n plus 1 times n squared plus 1. So I start from here now. And now I already know that this number is divisible by 6, so I don't have to bother about it. But I have to show that this number is divisible by 5. Why is this here divisible by 5? Well, we have to consider cases. You see here on screen, we have 5 possible cases about our n. And I will use the same colors here. So, case 1, if n itself is divisible by 5, then case closed, right? Because we have factor n here. If one of the factors in factorization of our number is divisible by 5, then the entire number is divisible by 5. So it is okay, because the factor n is there in factorization. Now, case 2 is if n is of the type 5k plus 1, right? Then what happens now? If n gives remainder 1, if in division by 5, then n minus 1 is divisible by 5, right? Because if we subtract 1 from both sides, we will get that n minus 1 is actually a number which is divisible by 5. So in this second case, this guy here is divisible by 5. So it is a number divisible by 5 times some integer. So the entire product is divisible by 5. What about the next one? The next one, case 3, is if n gives remainder 2 in division by 5. Well, n minus 1 will then get remainder 1, n remainder 2, n plus 1 remainder 3. So all our hope is in n squared plus 1. Okay, so let's see what will be n squared plus 1. Here I plug in, instead of n, 5k plus 2. And now I will use a formula which I didn't use yet. It is the formula for the square of sum. This is the first one squared plus 2, the first times the second, plus b squared. And I will apply this formula with a equal to 5k and b equal to 2, right? So what do I get? I get first, the square of the first one will be 25k squared, then doubled product, 2 times 2 is 4, times 5 is 20k, and plus 2 squared is 4, and then I still have plus 1. And you see 4 plus 1 is 5, so I can actually factor out 5 here, and here I will get 5k squared plus 4k plus 1. So this number n squared plus 1 is clearly divisible by 5. N squared plus 1 is divisible by 5 because it's equal to 5 times some integer. So in case 3, we get n squared plus 1, which kind of saves us. Now we get case 4. Case 4. If n gives remainder 3 in division by 5. So if it is equal to 5k plus 3 for some integer k. Then again, n minus 1, n and n plus 1 will not be divisible by 5, but again n squared plus 1. N squared plus 1 will save the situation. How? Well, exactly the same computation. So here you will get 5k plus 3 instead of plus 2, and here still plus 1. And application of exactly the same formula, but with a equal to 5k and with b equal to 3. So we get here 25k squared plus 5 times 3 is 15 times 2 is 30. K plus 9 plus 1. And here we see 9 plus 1 is 10, so we see again that it will be nice. It will be 5 times 5k squared plus 6k. 10, it is 5 times 2, so it will be plus 2 here. So we see that in this fourth case, n squared plus 1 is divisible by 5. And now we have just last case left, which was written in black color. Case 5. Case 5. If n gives remainder 4 in division by 5, then you see n plus 1. N plus 1 is equal to 5k plus 5. It's clearly a number which is divisible by 5. So you see in the method 2, we have analyzed 5 possible cases, and you know that that's all. There are no other cases. Of course, this k, I just wrote it k in each of the cases, but it can be just any number, any integer number, right? I could use another letter, but it doesn't matter. These cases are separate from each other. Here in all these cases, k is just some integer number, doesn't matter which one. So in all the possible cases, our number is divisible by 5, and divisibility by 6 was already proven in the beginning. So we are done here. Thank you for watching. Bye bye.